week, our guest speaker is Professor Tengyu Ma. Tengyu is from computer science department, also statistics department, and he worked broadly in the field of machine learning, and his research includes topics in non-convex optimization, deep learning, and this theory reinforcement learning, distributed optimization, convex regularization, high-dimensional statistics, and etc. Tengyu received his PhD from computer science department at Princeton University, where he was advised by Professor Sanjay Arora. Tengyu has received numerous awards, including Best Student Paper Award, and so on and so forth. So Tengyu is going to talk about data-dependent regularization and the generation bounds of neural nets.
Oh, somehow there's this let me see. I think there's a bug in this Yeah, okay, cool. Okay, cool. Yeah, thanks for the introduction. So I guess recently in the last few years, I was, I've been thinking about deep learning for a long time and the theory of deep learning. And recently, I've been kind of particularly interested in the statistical aspect of deep learning. So I guess that's probably particularly kind of relevant to this course. So I'm going to talk about these generalization bounds of neural networks and why they're interesting. So I guess I'm not quite sure about the general background of the students in this class. So I guess maybe some of these kind of like slides are assumes a little bit more knowledge than I supposed to assume. So, but please feel free to stop me at any point. So I guess a few years back, I think probably 2 years ago and 3 years ago, I was thinking about this optimization question, which is not what we are going to talk about. But I will start with it as a starting point or kind of as a motivation because 2 years ago, I was at Facebook. So I wanted to do some experiments, and before that, I tried to do a lot of optimization work, try to understand how non-convex optimization can work and how to speed up non-convex optimization. So because for all of this deep learning, the objective functions you are facing are non-convex. So that's the question I was thinking 2 years ago, and then I realized that there's actually so how do we design faster optimizers for deep learning? And I realized that actually it's not that hard to design a faster optimizer. The only thing you have to do is that you can just use small learning rate. So of course, there's a caveat here. It's difficult to have a fast optimizer, but here the point is that if you just care about the training error, you just care about making your training error decrease as fast as possible, then there are ways to make learning rate small. There are ways to make it faster. So for example, you can just use small learning rate. So actually, there are many other ways. I was involved in some of these papers that try to speed up the optimization, and it turns out that optimization. But there's a caveat. The caveat is that you speed up the optimization, but then the problem is that the regularization, the generalization is not as good. So here is a plot which I did quite a few years back. So when I discovered this issue, of course, this issue was discovered by many other people as well, and they are published in papers. So here, let me parse this plot with you. So there are two algorithms running here. So one in color orange, which is an algorithm with initial learning rate 0.01. And the green one is the algorithm with initial learning rate 0.1. So the learning rate, initial learning rate are different, and all the other things are exactly the same. And this is a very standard algorithm. So you just use stochastic descent with momentum, so on and so forth, and your new learning rate at some point. So these two algorithms, and you can see that the orange one, the dotted line are the training errors, and the solid lines are the test errors. So you can see that in terms of the training errors, the orange line, the line with small learning rate, converges much faster. Actually, it converges, to basically zero training error after 100 epoch. 100 epoch is the time that we change the learning rate. We decay the learning rate by a factor of 5, or by a factor of 10, I think in this case, at 100 epoch. And you see that with small learning rate, it converts fast at the beginning, and also it achieves zero training error very fast after 100 epoch, after a needing learning rate. So in terms of tuning, the orange one is outperforming the green one. However, in terms of the validation error or test error, the green one at the end of the day actually beats the orange one by like 1% or 2. So and this 1% is all that matters in some sense, because we already kind of get into the 5% regime. And if you kind of like play with this, you can actually see bigger gap between different algorithms. So and what is worse is that not only changing learning rate will make your generalization error worse. There are many other ways. So I think I was involved in several papers on kind of designing how to optimize optimize deep learning models faster. And we have theories to support the fast optimization. We have experiments that supports the fast optimization. And then at the end of the day, if you run all the experiments, the optimization is faster, but the generalization is not as good. So all of this suggests that the algorithm can regularize, which is a good, a nice, a new phenomenon to study. For research, you want to kind of have some new things to study, and here the new thing is that the algorithm itself can regularize. So the large learning one, even though they are optimizing the same objective, these two algorithms are optimizing the same objective. Actually, the large learning rate optimizer has a better regularization effect. However, the lack of understanding of the generalization also hampers the study of optimization. I guess I've convinced you about that, because we've tried different kind of algorithms. They optimize faster, but then at the end of the day, the generalization is not as good. So it's very hard to study optimization these days, because you may have a better algorithm, but it doesn't generalize. So nowadays we have some explanations for this, but it's kind of complicated. And today I'm going to focus on the understanding of generalization in deep learning. So I hope I convince you that even you just care about optimizing things faster, still you have to care about generalization, because that's the metric you care about at the end of the day. So just to have some kind of like a background or like a quick summary of what people have understood in the past few years about optimization. So I think we call this kind of algorithmic or implicit regularization from the algorithms. So the overall kind of like effect or the phenomenon we try to explain is the following. So suppose you have an over-parameterized regime, right? So you have more parameters than number of samples. Then the issue with this is that there exist multiple solutions that can fit the training data perfectly well. As you can see in the previous plots, right, the two algorithms found two different local minimum, and both of the local minimum have training error 0, but they have different test error. So one of the seminal work by Zhang et al. From Google and Berkeley people, so they found that if you use the same architecture and the same algorithm, actually can do these two things, simultaneously with the same algorithm. So suppose you train with data with real labels, then you can have perfect training error. And this is not surprising, because we have seen the perfect training error in the previous plot. And however, suppose you train with data with random labels, then you also can have perfect training error. So this suggests that if you have big enough model, then you can memorize all the random labels if your data has random labels. So the architecture clearly is not small enough to regularize. The architecture is actually very, very big, so that we can memorize anything we want. So however, if you train with the real data, what happens is that the generalization is actually good. So why that's the case? So the hypothesis is that the architecture is not what is regularizing. What is regularizing for us is the algorithm, like stochastic mean descent. So the hypothesis is that if you use stochastic mean descent with proper initialization and learning rate, then this algorithm actually prefers to converge some low complexity solution when it exists. So it's not that the algorithm is trying to converge to any solution with zero training error, but actually the algorithm has a preference in terms of which local minimum you want to converge to. So I guess just to parse this in more depth. So this with proper initialization and learning rate, this emphasizes that the algorithm or even the hyperparameter of the algorithm could matter, right? So not only just which algorithm you use, but also what parameters you set to, in the algorithm matters in terms of the generalization. Oh, I think there's some delay. Okay, so and also we say it prefers converging to a low complex solution when it exists. So this emphasizes that the intrinsic complexity of the data also matters. So if you have data with random labels, then there's no low complex solution that can fit the data. So that's why you're going to overfit, right? So of course, with random labels, you have to overfit. So the reason that it doesn't overfit with real label is that with real label, there exists indeed intrinsically a low complex solution that can fit the data. And that's that's the solution that stochastic gradient descent actually find instead of the solution that overfits to the data. So yes, as I said, if you have random labels, then there's no low complex solution. So that's why we're going to overfit. And on the other hand, we have a low complex solution, then we don't overfit. So just to kind of give a few examples where we can understand this kind of algorithmic regularization in a pretty formal way. So I had a hypothesis before, and this hypothesis can be fleshed out in certain simple cases, as we know now. So one of these cases is linear regression. So there's nothing to do with deep learning. We start with even linear models, and we know that with linear models, you already see some of this effect. If you use stochastic descent with zero initialization, then it converges to a minimum L2 norm solution. So in the objective, you don't regularize L2 norm. You don't do anything about regularizing. You just have the standard mean squared error, for example, or substandard. For linear regression, I guess you use mean squared error. So the only thing you restrict is that you say I'm going to use gradient descent or stochastic gradient descent, and I'm going to use zero initialization. So these two are enough to effectively act as a regularization technique. You are actually converging to the minimum L2 norm solution of the data, and a minimum L2 norm solution that fits the data. So and the idea is basically that because you are using gradient descent and with zero initialization, your parameter actually only stays in the span of the data. So the algorithm actually has a limitation. The algorithm cannot leave the span of the data. So the limitation actually helps us regularize, right? So in all of these machine learning cases, the reason I generalize is because either your algorithm or architecture or something has a limitation so that you cannot overfit to the data. And here the limitation is that the algorithm cannot leave the span of the data. That's why it has some regularization effect. And the second example is this logistic regression case, where you have classification problem. You have like a binary label, for example, and again you can use stochastic gradient descent or gradient descent, and it has been shown by various people that if you use gradient descent and then it converges to the max Martin solution. I'm not going to define formally the max Martin solution here. I guess probably some of you have seen it in the machine learning classes. Like max Martin solution was studied extensively before the deep learning era. Like this SVM kernel machines. These are all based on the max Martin solution. So basically, you have some preference on the model, right? So if you don't know what max Martin means, it's some kind of like a special property of the solution. So it's not, but we never kind of enforce this property in the training. However, the gradient descent algorithm encourages it in a non-trivial way, right? So this is not written in the loss function, but the algorithm somehow prefers to converge to this kind of max Martin solution. So and in both of these two cases, we are still in kind of like the linear model case, right? So there's no deep learning involved. It's really just a linear model. So and there are and here is a case where you can extend some of this kind of linear linear models to nonlinear problems. So this is neural networks with quadratic activations. And it relates to matrix sensing, but if you don't see the connection, it doesn't really matter. So I guess probably some of you don't know what matrix sensing is. It doesn't really matter. So here is a setup. So suppose you have a neural network that generates the real label. So this is called U star. So you have a two-layer network. Actually, we also assume that the second layer just have weights or one weights, and the only variables are the first layer variables. And this is the ground truth that generate the label Y, right? So in some languages, it's called a teacher network, or you could call it ground truth in statistics. And when you learn it, you are not going to use this small model. You are going to use a big model. So you're going to use as many neurons as possible if you want. So you say I'm going to have m neurons, and m potentially is a very, very big number. And I'm going to use this over-parameterized model to learn the data that are generated from the small network. So, and a priori, if there's no regularization from the algorithm, you may think, okay, this will overfit because at least I need to have d times m number of parameters to learn such a model, because at least I need to have d times m data points because I have d times m parameters. So, but actually that's not the case. So we can show that actually how many data points you need to learn this model doesn't depend on how many parameters you need, or how many parameters you have in the model. So the data point, the sample complexity depends only on the ground truth, as you will see here. So basically, for any m that is bigger than r, so as large as possible, as you want, if you use gradient descent with small initialization, actually, there's a preference of gradient descent. The gradient descent converts to the minimum forbidden norm solution if there exists a small forbidden norm solution. So we have assumed that U star is small, and with only 2 neurons, the forbidden norm is small. So actually, even you have a very over-parameterized model, you are going to find the minimum forbidden norm solution when such a U exists, and the sample complexity is only d times r squared. So you don't need to pay d times m data points to learn such a big model. Actually, only you have to pay d times r squared number of samples to learn this data set. So the intrinsic complexity of the data set matters, because the intrinsic complexity of the data set is of something that depends on d and r, and that's the only thing that matters in the sample complexity. Okay, so and this is showing one of the papers that I have with some collaborators, and I guess this is probably the most involved setting that we can analyze these days. And you can see that the setting is very, very simple. You only have 2 layers, and actually 1 layer is already fixed. So, but that's the best we can do pretty much in terms of like the complexity of the models we can analyze. So there are a lot of open questions. For example, what happens if you have multiple layers? What happens if you don't use quadratic activations? You can use ReLU activations, so on and so forth. And we pretty much expect that this phenomenon is somewhat true even for multiple layers and other activations. But the issue is that what's the complexity measure? So here we say gradient descent converges to the minimum forbidden norm solution, and we have multiple layers. It's not clear the forbidden norm is the right measure for the complexity measure, and that's something we don't know, and it's a big open question. So the fourth thing I like to kind of mention as a kind of like a background, or kind of like a this is always good to know technique. So this is called neural network with large initialization. So by large, I mean I think I wouldn't quantify exactly what large means, but it means like larger than what we are using right now. So if you use larger initialization than what we are using right now in practice, then here's a theorem that you can show. So well, let me parse the sentence. So for any large enough with amps, right? So you have you want the weights to be as large as possible. And then gradient descent with a certain initialization, by certain initialization I mean larger than what we do in practice, then this algorithm converts to a function that fits the data perfectly with minimum norm in the RKHS, the reproducing kernel space defined by neural tangent kernel. So I guess there are a lot of things that I didn't define for the sake of simplicity. What is neural tangent kernel is some kernel that is induced from a network, which probably I wouldn't define formally, but it's a kernel. So basically, the idea is that if you use gradient descent, the best you can do is basically the kernel method with this neural tangent kernel. So and you're going to converge the minimum norm solution measured by the norm defined by this kernel. So the reason why I'm not going to kind of like formally define all of this is because I'm going to show that this is limited, because the reason why this is limited is because the initialization is chosen so that the initial output is, so the initialization, just to be precise, is chosen to be on the, so that the initial output is on the order of 1. This is larger than what we usually do. And the reason why I'm not going to kind of like formalize exactly all the details here is because my personal view here is that these results are not the best we can achieve with neural networks. So people have empirically and theoretically found that the initialization shouldn't be that large. So if you use small initialization, then you can achieve better generalization. So this is another example where you can see that the initialization and the learning rate both matters in deep learning. So which algorithm you use, even what specific parameters you choose for the algorithm can change your generalization performance, even though all of these different choices could lead to the same training error. So and you will see, empirically people have found that small initialization would work much better, and theoretically we are going to have a theorem that says that if you use small initialization, you are going to have better generalization. So basically, I think in the last 20 minutes, I was basically discussing this algorithmic or implicit regularization point of view. And just to repeat the hypothesis is that if you use stochastic descent with proper initialization and learning rate, it prefers to converge to some low complex solution. And what does it mean by proper and initialization and learning rate, and what low complex solution, we don't really know. So here, so in other words, there are two missing components in this hypothesis that we don't really know for deep learning. So one thing is that we don't know exactly what the right definition of complex measure, and which complex measure can imply the generalization. So in all the previous examples, I have used several different complex measures. For example, the norm, the L2 norm, the max margin solution, or the forbidden norm solution in the quadratic neural network case, and also the RKHS norm in the slides before. So they are all different kind of like complex measures that are proposed to measure the complexity of the networks, and they all make some sense. But most of these complex measures are for either linear models or two-layer networks. So we don't really know what exactly the right complex measures we should study for deep models, for example. And that's one question we are going to answer, at least partially answer in the rest of the lecture. So, and another component is that if you have the right definition of complex measure, how do you show your algorithm has a preference? Right? So how do you show the algorithm has a preference to converge to a low complex solution? And that's often also very challenging. So, I guess, all the complex measures we have discussed so far are basically Euclidean norm solution, Euclidean norm. So the L2 norm of the linear model, the forbidden norm of the weights, all the RKHS norm, they are all fundamentally L2 norm. And I think we have to kind of move beyond L2 norm at some point. So, and in terms of the second component, I think in the examples I showed 1, 2, 4, basically the example 1, 2, 4 I showed, basically this analysis of the algorithms are only using convex optimization tools. So pretty much you are just still live in a world where the objective function is convex, and only in the example 3 where we have quadratic networks with 2 layers, we are kind of doing non-convex stuff. And for deep learning, intrinsically you are kind of optimizing a non-convex function, and we don't really know how to analyze non-convex functions very well. So this is another example where the optimization and generalization kind of interact with each other, because to understand whether you can generalize, you have to understand how the algorithm performs, how what the iterate or the dynamics of the algorithm looks like. So, and even in this kind of non-convex case that we can analyze, if suppose some of you are interested in the techniques here, so the techniques are still limited. So the techniques we use to analyze some of these algorithms is still based on eigen decomposition first of all, it's very involved, in my opinion. And second, I think the techniques probably are not exactly the right techniques for the future, because when you have multiple layers and different kind of activations, the eigen decomposition is not the right tool in some sense, because you don't have linear algebra anymore when you have deep models. So and this is a major tactical issues with all of the deep learning, because we cannot really leverage the linear algebra anymore when you have deeper models. And this technique is still based on linear algebra, which means that it's somewhat kind of limited. Okay, so I guess just to summarize, this hypothesis, of algorithmic or implicit regularization, in some sense, is a combination of two things. Right? One part is you have to analyze the algorithm, and the other part is the generalization theory of networks. So on the left-hand side, we see a lot of difficulties. I guess I will just repeat some of this. The algorithm is very hard to analyze, and sometimes there's an intractability issue, because analyzing the algorithm, converging to a global minimum of a non-convex function is intractable. Even converging to a local minimum is technically intractable. So and often to kind of go beyond intractability, we have to require very strong assumptions on the data distribution in the non-convex cases. So you have to assume the data are somewhat kind of very nice, and so that optimization is not too hard, so that you can kind of go beyond the intractability results. And also the question is, if you kind of like think about the algorithm organization, one limitation is that even if I understand at some point why the algorithm has a preference, right? Still, it's not exactly clear how do you manipulate your algorithm to get better generalization, right? You may know how to manipulate the initialization and learning rate to get better generalization, but you may not be able to change your algorithm in a way that makes the generalization better. So and this is the main issue, because so at the end of the day, we don't want to just tune the learning rate and initialization, right? So we want to change our algorithm, and we don't know, so basically, if you go with this route, then for any algorithm you propose, you have to show what's the preference of this algorithm in terms of the complexity measure. So basically, every algorithm result probably would have to have two parts. One part is about how the training error decays, and the other part is about how the inductive bias of the algorithm, or what kind of regularization effect of the algorithm has, that algorithm has. So I think for the second part of this lecture, I'm kind of like I like to kind of like convey this my view about this. The view is that probably the right way to go with the analysis is not to do this two-part thing, like the algorithm and generalization. So maybe the first part is too hard, and anyway, because you need a second part, then we just focus on the second part. And so first of all, if you only focus on generalization, right? So you only want to understand the statistics of the model, right? So what complex measure would imply better generalization? Then anyway, understanding this is necessary in this old plan, right? So in the old plan, you have to combine these two parts anyway. So anyway, we have to understand the generalization. And second, perhaps you don't have to really care about the algorithms if you don't if you can somehow avoid the algorithm organization. So here is the idea. So if you have figured out what a complex measure is for the generalization, then you can just say, I'm going to add a complex measure as the regularizer. So I'm not going to rely on the algorithm to regularize. I'm just going to proactively add a complex measure to the loss function so that I can have generalization. And this way, you don't understand why the algorithm can regularize, but you can still get regularization because you add a complex measure as a regularizer in the loss function. And sometimes this is a kind of like a proactive way to manipulate your regularizer, because you can add different regularizers as you wish, and to see which one has a better regularization effect. And this is probably easier than manipulating the algorithms. And in some sense, one of the benefits of this is that you can achieve some separation of concerns, because now the idea is that we're going to train with a regularized objective without worrying too much about the generalization. Without worrying too much about the generalization and the implicit bias of the algorithms. So basically, all the regularization effect comes from the loss function and the regularizer, and the algorithm is just for training. So we can separate the training with the statistics, because the loss function and regularizar takes care of the statistics, and the algorithm is only for getting low regularized training loss. So this is in some sense like my my recent view on how to go, at least how to have like an immediate practical impacts when we do theory. So if you analyze the algorithm, perhaps it takes a long time to understand how the algorithm can regularize, but this approach probably would lead to kind of more fruitful. Hopefully, I think it can lead to more fruitful and short-term kind of impact in some sense. So, and also, of course, the limitation here is that you have to assume that training is successful. So you just say, okay, I don't know how the algorithm can work, but I just assume the training of the algorithm can find me a good local minimum, a good global minimum. So this is a big assumption in this plan, but with this assumption, then we can reason about other things. Okay, so I guess what I'm going to do next is that I'm going to talk about some of the recent results in my group that kind of execute this kind of general plan about only understanding the generalization and adding it as and adding the complex measure as regularizers. So before that, any questions? Okay, so I guess generalization bounds of deep networks. So I guess the rest of the talk, just to have a quick overview. So we're going to talk about two different complex measures and regularization for deep networks. And one thing is about norm-based complex measure, and the other thing is about data-dependent complex measure. So I guess by generalization theory, what we mean is really the following. So we want to prove that the generalization is less than something like of this form. So it's a square root of the complex measure over margin times 1 over square root n. So this is typical in statistical learning theory. I guess by generalization, I mean the test error minus the training error. And complexity is something we are looking for. So we are looking for the right measure of the complex measure. And the margin is just the standard definition of margin, the largest output minus the second largest output, or basically the number you put in before the softmax or logistic loss. So this is something that we don't change. So the only thing that we change is looking if you know slow rate and fast rate. The reason why we only care about slow rate is just because these are results we can obtain for the moment, and in the future probably we can scale up some of these results to faster rate. So I guess maybe I'll skip this just for simplicity. So the norm-based generalization bounds. Okay, maybe I can talk about this a little bit. So this slide, main point is we can show that L2 regularization is better than no regularization, and you can have simple situations where if you use L2 regularization, you can get better sample complexity than if you use no regularization. So this is a situation where it's a very simple data set where you have kind of a d-dimensional data set, but only the signal are from a two-dimensional subset of the coordinates, and basically in this dimension I'm plotting all the d-2 dimensions, and this dimension is never really useful, and you only have to look at the two-dimensional subspace, and you can classify the examples into two groups, right? So these are the red ones and are labeled 1, and the blue ones are labeled 0, let's say. So and for this data set, we can, even this simplistic data set, we can show that the complexity, so the number of samples you need to learn this data set with L2 regularization is going to be something like O of D. Of course, you have to set things in the right way, so you have to use cross-entropy loss, L2 regularization, and assume the optimization succeeds, then you can show that the sample complexity is pretty good. It's only d of d. But if you use no regularization, which means that you are using this so-called neural tangent kernel technique, then the sample complexity is d squared. So this is a very kind of toy example where you can see that the regularization is important when we use this model.
Is it regularization on the weights or on the activations?
Yes, so here is, and I'm going to talk about the regularization on the activations, which is actually more interesting.
And also, is it something that people use, like practitioners, they use this type of regularization?
L2 regularization? Yeah. So to apply a little bit L2 regularization. So that's the standard, very standard technique. For NLP, I think people still use L2 regularization, but very weak regularization. So, but you have to use it. It's something very small, like the coefficient before the L2 regularization in NLP case is something like 1e minus 6 or something like that. But you cannot really drop it to get the best result, I think. At least in certain cases that I'm familiar with, we've tried to drop it, and it doesn't work. And also in NLP, I think there are also stronger regularizations as well, like dropout, so on and so forth. So, I guess the short answer is that we need to use regularization, at least some small amount of regularization in practice. Activation means the hidden layer of. Oh, in this theorem. I think this activation is ReLU. I think. I think, but the activation doesn't. Let me think. So.
I think for ReLU, the L2 regularization means open regularization on a function space, so that's why you can have such results on a sparsity structure function and regularization. So if you change the ReLU to other activation, I don't think you can have such results.
I think this result doesn't depend on ReLU that much. I'm trying to think how general we had. I don't think the result depends that much on ReLU. Of course, you need some assumptions. It cannot be linear, for example. Probably we only proved it for ReLU. I forgot exactly, but definitely I feel like it can be extended to other activations as well. We are not using those strong characterization. So first of all, even you use ReLU and you regularize the weights, it's not clear what's the inductive bias in the functional space. You cannot, it's very hard to characterize that exactly. We are not using those results as a building block.
So in the theorem, besides the optimization part, did you rely on how wide the hidden layer?
We did. So you need it to be as so. Even to get the upper bound, of course, for NTK, you need it to be wide, right? So that's why how you get NTK results. But for the L2 regularization, you also need it to be wide enough because. Okay, I think maybe fundamentally you don't need it to be very wide, but the results are proved with very wide networks. So there's a little bit of convenience if you say the width of the network is bigger than the number of samples. Yeah. Yes, and generally I believe that even if you use regularization, still and even if you don't care about optimization, you just care about statistics. Generally, I believe that wider networks still has a benefit, and the benefit is because I guess technically the benefit comes from that when you have wider network, you actually can have bigger margin. So, and if you have bigger margin, you have better statistical guarantees. But we can talk about offline probably. Okay, so so now I think this also relates to one of the questions that people ask about whether we are regularizing the norm of the weights or regularizing the activations. So so if you just only care about the weights, and these are the best results for deep models. So the previous result was only for 2-layer networks, and here are the best results for deep models. So in Golovich et al., I think they considered the product of the L2 norm of the weights. So this is the complex measure, right? So everything is was on the denominator, numerator here is always the complex measure. So that complex measure is the product of the L2 norm of the weights. So and of the weights of different layers, right? So and in some other works they have different kind of complex measures. For example, the product of the spectral norms of the weights and times something else about the sum of the norms, which is not necessarily very important because I think the product actually dominates everything else because when you have a product of a lot of things, then you can have exponential growth. So, maybe I'll skip this point. So the question is, whether we can find better complex measure or better regularization, right? So I've tried to convince you that regularization is important, and now we care about how do we regularize in the best way. So an existing analyzable regularization of complex measures mostly depends on the parameters, right? So you regularize the norm of the parameters, the L1 norm, L2 norm, so on and so forth. So, but actually, if you think about it, actually in deep learning, you can regularize a lot of other things other than the parameters. For example, you can regularize the norm of the hidden activations, right? So which is not only a function of parameters, but it's a function of both the training data points and the parameters. So, and if you have such a regularization, then we don't know how to analyze the statistical performance of such a regularizer's effect to the statistical performance. So, and actually there are many other empirically successful regularizations that depends on both the parameters and the data. So actually probably all the successful regularizations except L2 depends on both parameters and the data. So for example, dropout, which is the influence of dropout, is through both the training data and the parameters. And if you do batch normalization and layer normalization, these are these days believed to be to have a regularization effect, and they depend on both the training parameters, both the parameters and the training data. And I guess probably not all of you are familiar with this recent techniques about mix-up, which is a data augmentation technique, which is also a way to manipulate both the training data and the parameters to regularize. So, if you don't know it, it's fine. This is just another way to regularize a quantity that depends both on the training data and the parameters. So I guess just to convince you that batch normalization actually can regularize. So this is some plots that we had in one of the other papers, which is not too much about regularization, too much about batch normalization. And so in the paper we try to find out a different way to regularize instead of using batch norm. And you can see that actually we didn't succeed in doing that. If you compare all of these curves. So batch norm is the blue one. Group norm is probably we can ignore group norm for the moment. This is just copy paste from the paper. So and fix up is one algorithm that try to not use batch norm. So the reason why we have to compare with fix up is that if you don't use any techniques if you just remove the batch norm from the existing model, then actually you cannot even train. So this fix up is actually fix up the training, but it doesn't fix up the generalization. And you can see that this algorithm, this green one, right? This is something we propose in this paper that makes that removes the batch norm, and this one can train much faster and batch better. However, if you look at the test error or the validation error, so the green one actually has the worst validation error. I guess this is just another example for a large-scale data set to show that training faster or training better is never is not doesn't really mean that you can generalize better. So you train faster and better, but you can generalize worse. And on the contrary, this shows that batch normalization has a regularization effect because it makes the generalization error or the test error smaller, but makes the training error bigger. So, and in the paper, we have found different techniques to kind of bridge this gap, and this is using this so-called mix-up technique, and then you can make the training and generalization both. You can make the training worse, but the generalization better. So, so I guess the point of this slide is to convince you that if you use some batch generalization kind of techniques, then they can regularize much better than without batch generalization. So, and if you remove the batch generalization, you have to resort to other kind of generalization, regularization techniques like mix-up to fix the generalization gap. So this kind of motivates us to analyze regularization techniques that can depend on both the parameters and the training data. Batch generalization is one of them, and there are many others. And the goals, basically. Of this kind of like a line of research is that we want to find new mathematical tools to handle data-dependent bounds, data-dependent regularizations, and we hope that better generalization bounds with data-dependent complex measures can be derived, and then we apply this complex measure in the experiments, and we hope that empirically we can regularize the complex measure for better accuracy. Or we don't get better accuracy, but we just want to reduce the influence of the algorithms, because as I argue that the regularization effect of the algorithms is kind of like a double-blade sword, because it helps us, but also it's hard to manipulate. So we want to reduce the influence of the algorithms and replace the influence of the algorithms by the complex measure, so that by the explicit regularizers, so that we can manipulate the regularizers to get better generalization guarantees. So I guess what we have done was that we proposed some generic approach to have better mathematical tools, and we remove the dependencies on the depths, exponential depths on the, or remove the exponential depths on the dependencies in the previous generalization bounds. I guess I didn't emphasize that in the previous slides. So all the existing bounds depends on exponentially on the depth of the network, and we remove the dependencies. And also we have some preliminary improvements in various settings in terms of the empirical performance. So if you add the complex measure to the loss function, you can regularize better and get a better generalization performance. So I guess just to have a very quick kind of like introduction about what data-dependent generalization bounds or data-dependent quantities we use. So one of the quantity that we regularize is the L2 norm of the hidden layer of the training data. So this is a function of not only just the parameters, but also the training data. And another thing we regularize is the maximum operator norm of any interlayer Jacobian. So you look at I and J. So let me parse the notation here. So we have a network, and the layers are numbered as H1, H2 up to HR, and the weights are numbered as W1, W2 up to WR. And you can take I and J. So I is bigger than J. So you have a higher layer. You take the derivative of HI with respect to HJ, and this is a matrix, and you measure the operator norm of it. And you take the max over all possible pairs of intermediate layers, and then you take the max over all training data. And the point here is that you take the max over all training data, so that this is a quantity that depends on the training data, so that you can compute it on your data points. So and there's some quantity about margin. I guess now I'm defining the formula what the margin is. The margin is basically the output for the correct label minus the output for the second largest output, minus the second largest output. So basically, this is how kind of confident you are with about the correct label. So if your margin is big, that means that your output for the correct label is much bigger than the output for the largest second largest label. That means that you're somehow confident. And we'll also assume the training error is 0 because we have over-parameterization. So if you have so many parameters, your training error is always 0. So and the bounds that we can get is the following form, which looks a little bit complicated, but let me parse it for you. So there are some quantities here which is about weight matrices. So that's why it's not very important. So what's important here is here. So the point is that this is a polynomial in R and sigma and T. So what is R and sigma and T? So R is the depth, sigma was the Jacobian norm, and T was the norm of the hidden activations. So I guess just to compare with previous bounds, so previously people had the product of the spectral norms. And this is a quantity that is not a product of R quantities. It's only a polynomial in a certain number of quantities. So before it was exponential quantity, and now it is reduces to a quantity that only is polynomial in some of this R sigma t. I guess just to show that this new bound is conceptually better than the old one in many cases. So if you think about what is T and R and sigma, so T is the maximum L2 norm of any hidden layer of the training data. Right, so this is T. If you relax T a little bit, you say I'm going to upper bound T by the max over all possible inputs with norm 1, and then this is less than the product of spectral norms, because if you because that's the maximum possible. It's an upper bound on the maximum possible hidden layers you can have, right? So because each layer you can only make your hidden activations bigger by something like Wi operator norm, and and you take the product of all of its layers, and that's the biggest hidden layer norm you can get from this. So that's why this quantity T is smaller than the old quantity that measures the complexity. So and similarly, if you have the maximum operator norm of the interlayer Jacobian, then you will have you can do some inequalities and show that it's also lower than the quantity that we had before. So in some sense, this is a worst case estimate of the quantity sigma and T, and we are just replacing the worst case estimate by some quantity that is more kind of realistic and smaller. So I guess I probably will skip some of this, and just for the sake of time. So maybe we can kind of like, so we introduced this new complex measure, and this new complex measure, we want to kind of see whether it has better correlation with the test error. So in this plot, we are showing several experiments. So and in the x-axis we have the test error. In the y-axis we have the log of the complexity. So and we have different algorithms and different architecture, different models that we are trained using different algorithms. So so we use actually there are three models. One is using batch normalization, one is using fix-up, and one doesn't use any batch normalization. And we have two complex measures. One is the spectral complex measure, which is the previous complex measure that people used. And ours is the complex measure I talk about, which involves the hidden activations and the Jacobian norm. Yes. So I guess you are referring to some of this complexity, the compression bound, right? So the limitation of those bounds is that they only works for the compressed model. So it's kind of like a postdoc thing. So suppose you give me a model and I can compress it, and I know the compressed model can have good generalization, but I don't know whether the original model have good generalization. And why you care about the original model has a good generalization? A, probably you don't want to compress every time, and B, you also want to regularize the original model during the training. So during the training you cannot compress and regularize the compressed model, right? So you have to somewhat kind of regularize the original model. So I think that's the difference. Okay, so I guess the plot shows that the complex measure here that we propose has a better correlation with the real test error. And actually, you can see that the previous complex measure is very weird. So if you have test error, something like here, so suppose you have a model like this, and you measure the complexity, actually is 2 to the 16. So it's very big, but actually the test error is the best. And at least for our case, we can see that when the test error is the best, then your complex measure is also small. And actually it's only like 10 to the 6, which is not very big, right? So, all right. So and how, okay, so this is okay. So far what we have discussed is about how do we regularize the So what's the complex measure that can guarantee good generalization, right? So and after we figure out the complex measure and we try to use the complex measure in the algorithm in the training. So how do we regularize the complex measure? So the hidden layer norm. So recall that the complex measure depends on two things. One is sigma, and the other is t. So the t is the hidden layer norm, which is already regularized by the normalization layers. So because you have normalization, so the hidden layer norm is already kind of fixed to something like 1. And so the only thing you have to regularize is the interlayer Jacobian norms, something like a derivative of hi with respect to hj. And what we do is we just add this complex measure in the training during the training, and we see that the in various settings the generalization performance empirically get better. So so I guess just to parse this table, so basically so in this column we kind of indicate whether we add a regularization. So if there's no regularization, we use cross, and otherwise we have yes. So and if you compare these two, after adding regularization, we improve by something like 0.5%, and here we use a smaller than rate, and the generalization is worse, and after adding the regularization, we can improve by 0.5%. So similarly, I think in other cases where you don't have data augmentation, we can improve by 2%, and if you have no batch generalization, you can improve by somewhat like 1.1%. So basically, the point is that with this correct complex measure, with this kind of slightly better complex measure, and by regularizing it, we can get better generalization performance empirically. And also we have a recent work, which we just submitted to iClear. So we also kind of extend the notion of the margin. I didn't discuss the margin too much. So the margin that we used was the largest margin minus the second largest output. This is the notion. So this is called the output margin, and we extend it to all layer margin, which is a better notion of margin in our opinion. So the benefit of having this better margin, which I'm not defining, so you can, if you're interested, you can see the paper. At least you can find one version of the paper online. So with this new definition of margin, which I didn't define, we can simplify the proof and have better empirical results. And here you can see that we have clearly in all of the settings we can have better results, right? So compared with the standard SGD, we can improve by like something like 0.6%, and in many other settings we can improve. So I guess we consider different architectures, different settings, for example, whether you have data augmentation or not, or whether we have random labels. So in all of these settings, we get a better improvement. Okay, so I guess I'll spend probably like 5 minutes to discuss a little bit about the technical challenge to get this kind of data-dependent bounds. So I guess some of this can probably depends on requires a little bit kind of backgrounds on the statistical learning theory. So I will just briefly summarize them. So the standard uniform convergence bound that you use to derive this kind of like a theorem is that you say I have a family of hypotheses with some property. So this is, for example, the family of hypotheses with product norms of weights is less than something. So you say this is the property that I care about, and I kind of prescribe or describe a family of hypotheses with this property, and then you show that for all of these hypotheses, the test accuracy and the training accuracy, or the test error and training error, are not different too much, depending on some complex measure. G of R over square root n. So this is the commonality of all the previous kind of like a generalization bounds. You care about a family of hypotheses, and you prove that the training error and the test error are not very different on all the hypotheses you care about. So in some sense, the kind of the mental the picture in my mind is that you have this training error. Suppose in the y-axis you change your parameters, and you have tuning error and test error. So so you want to say that the tuning error and test error are always close in this sense. However, for us, we know that the tuning error and test error are not always close. So this is what I'm showing here. So the tuning error and test error are not close at every point. They are only close for certain subset of hypothesis. So wait. Okay, yes. So the issue that we have is that the set of hypotheses that we care about depends on the training data. So it's not like you care about all the hypotheses, because if you care about all the hypotheses, then this transition is not good. So you only care about a certain type of hypothesis where for example, the hidden layer norm is small and the Jacobian is small. So you only single out the subset of hypothesis, but the subset of hypothesis depends on the training data themselves. So for example, if the set of hypothesis is something like the hidden layer norm is less than R, so we have this data dependent set of hypotheses. So right. So the challenge is that this family of functions that we care about is a random family of functions that depends on the training data. If the training data are random, then this family of functions is random. So so the existing tools cannot deal with this kind of random hypothesis class because they have to care about the fixed hypothesis class. So I guess just another slide about how do we kind of address this issue. So the way that we do it is that we call it so-called loss augmentation. So recall that the previous framework, I guess a high-level kind of description of the previous ways to prove this Radamar complexity bound is that you say you have some complex measure of some hypothesis class, and you say this induces the complex measure of the losses composed with the hypothesis class, and then this implies the generalization. So I guess if you you're not familiar with the high-level thing, basically you say I have the complex measure of some hypothesis, and I can derive generalization. So and our approach is that we this is the standard approach, but this hypothesis doesn't depend on the data. And what we do is we say we're going to fold more data-dependent properties in the loss. So basically what we do is we say we change the loss function that we care about. So suppose you have a set of properties pi with some desired bounds gamma I, and what you do is you say you're going to augment the loss function in a way that you incorporate all of this hypothesis, all of these data-dependent properties in it. So basically if your function doesn't satisfy the data-dependent property, then you are going to basically change your loss function to be something trivial. So suppose my hypothesis doesn't satisfy this, doesn't satisfy that the property pi is less than gamma I, then this indicator will be 0, and then my loss will be 1. So basically, for all of those functions that are not in my set of, in the set that I care about, I will just set the function to be 1. So I guess maybe just pictorially, what we do is that say before we have that the test error and the training error are not close universally, so they are only close in a subset that we care about. And what we do is we say we are going to change the loss function outside the subset so that these two loss functions are close universally. And now we can apply the standard techniques on the loss function on the right-hand side. And we say these two loss functions are close universally, and in the subset, that means that in the subset they are close. And in the subset, the two loss functions are the same, right? So in this region, the old loss and the old loss and new loss are exactly the same. That's how we prove that in this region, the test error is close to training error. I guess I'll skip this. Probably I'll just conclude with this. I guess as a summary, so we have some data-dependent explicit regularization, and my view here is that if you do explicit regularization, it's still important because it's more powerful than neural tangent kernel, and it may replace and improve the generalization of the algorithms. So at least it may replace the effect of the algorithmic regularization, and I guess you can see that from our recent work, we can also improve the regularization from the algorithm. I guess the open questions are that whether we can get a better data-dependent regularization. For example, whether we can analyze some of the existing ones like dropout, data augmentation, or some of the new ones, and whether we can extend some of these techniques to more complex settings. I guess I'll stop here and to have some time for questions. Thanks.
Any questions?
So one question is, if you go back to the bound with I guess, like sigma multiplied r over gamma, empirically, like what would be the truth without like relying on mathematical detail? Meaning, if I observe the test error, what would be the best numerical fit by looking at the terminal?
What do you mean the best numerical?
If you forget about whether you can prove it, what would be your best guess of a formula? Is the type is upper bound or test error?
Oh, I see. What would be a better bound if I guess?
Yeah.
I don't know. It's very hard to guess. So basically, that's why we have to resort to the theory to, whatever we can prove, that's probably the best guess. I don't have other ways to guess what's the right complex measure, in some sense. So, and that's exactly what we did. We didn't know what the complex measure is. We just try to prove this bound, and whatever we can prove, we declare that's one complex measure we can consider.
So maybe a follow-up question on that is like, how do you come with, like in the research process, how do you come with an idea for a new bound, and then how do you go about proving it?
Yeah. So currently we are. So I guess there are probably two sorts of inspirations. So one part is very technical. You look at the old bound and see which part is not efficient. So like in which part like this bound is kind of not tight, in which part of the proof is not tight. But that's a very technical way. And the other way is that I think we have intuitions from the experiments. For example, what quantities are useful for regularization. For example, if you look at dropout and mix up some of this, that somehow the hidden activations are supposed to be small because otherwise you may overfit. So like we use other kind of like existing regularizers to get some kind of inspirations on what kind of bounds we are looking for. So I don't have a third kind of high-level approach, but actually, but I don't know. I don't think these two are the only way to kind of get better ideas about this. But I don't know what others are there.
So you described this general pipeline where you add the complexity measure you care about as explicit regularization in the loss, and then you don't have to worry about tinkering with the architecture, the optimization technique. But as you showed with the vanilla gradient descent on linear regression, that has some property of regularizing towards a certain solution. So if you say, okay, I'm going to put in my correct complexity measure in there, how do you know that even if you choose a simple optimization algorithm or architecture, those aren't going to be competing in some way? Like you're still using some algorithm that has some implicit regularization, and you're also building in your explicit one.
I see. That's a good question. So I guess just to repeat the question, I think you're asking, what if I add a regularization, explicit regularization, which is not doing the same thing as the implicit or algorithmic regularization, and then they compete with each other, right? So first of all, I think probably I think the explicit regularization in general should win because the algorithm is the main goal of the algorithm is still trying to minimize the training loss. So or the regularized training loss. So if the algorithm regularization should only exist when there's no any other tiebreakers. So and if you have a strong tiebreakers, the algorithm regularization should always kind of concede to the explicit regularizers. I think that would be the guess for most of the cases. And another way to answer this is that probably you shouldn't add something super different. So maybe there's no competition, right? It's probably more like it's A plus B kind of things. Like the algorithm is dealing with some regularization, and the explicit regularization is doing something in addition. Or you want a explicit regularization to subsume the algorithm back. But probably you don't want to kind of like introduce too much kind of competitions, because we know that the algorithmic version of the regularization the algorithm regularization is actually doing something good for us. So why we want to compete with it? Regularization techniques, and actually something like I sometimes call it non-parametric because if you look at this bound, the only way that the parameters come into play is this. So all the other bounds are all the other quantities are kind of like not really depend on the parameterization. So actually that's a nice thing about it because you only use the parameterization. It's a kind of hybrid thing. You use the parameterization to guarantee something, but you still care about the local curvature, the non-parametric things. So, but going back to your question, whether we have better rate, so I think in the new paper we do have a better rate. So, but the rate is a little bit complicated. That's why I didn't show it. So it depends on how you define your complex measure. For certain definition of complex measure, you can get better rates, and for certain definition of the complex measure, you can only get slower rate. Generally, I don't think we understand exactly what's the trade-off yet, but I'm just saying that it's possible to get faster rate in certain cases. Okay.
I have a question, almost the same question as this. So basically, I'm just wondering if in your experiment, did you try, different sort of algorithm just to make sure that you can, decouple the effect of
Yeah. Yeah.
Okay.
No, we didn't. So maybe I would like to finish the question.
Sure, yeah. So I'm just wondering if you try, different algorithms just to decouple, this explicit realization apart from, implicit realization. And another question of mine is actually that, your complexity measure seems to be something like, it has something to do with normalization of the training data. But we know that, we have convolutional neural network that is, that is good for images, for example, and other stuff. And do you have any insight into, things that are more relevant to the structure, inherent structure of the data?
Okay, so I guess for the first question, it's kind of easier to answer. The answer is that we try to see whether the explicit regularization can subsume or disentangle the algorithmic version. So in some sense, this is the plot that we are trying to do this, and you can see that we do it in some. We can achieve a little bit, but not. We can recover the loss of algorithmic regularization to some extent, but not all of them. So here, I guess, will be a comparison. So you say, suppose you compare this one, the batch norm version, with smaller than rate and batch norm, right? So these two, so basically these two experiments only differ by the learning rate. So the only difference is the algorithm, and you can see that you lose 1.5% from 4.4 to 5.9, and the hope would be that after applying the explicit regularization, you can recover all the way to 4.4, right? So so that you don't have to care about the algorithm. And what we can do is only recover to 5.4. So certainly we have a long way to go in some sense. And here, I guess this is the same thing. Suppose you remove the batch norm. Suppose you believe the batch norm is a regularization technique. You remove the batch norm, you can get to 6.6. You lose 2%, and we can recover 1%. So I think in the new paper we didn't have time to do the same thing, but I think in the new paper we're going to recover more. But my general take is that I'm not thinking this is a completely a replacement of the algorithmic one. They are doing something similar, but also doing something different. So this is an open question. So we achieved a little bit, but hopefully at some point we can replace all the algorithmic version and also do something better than that. And for the second question, I think you are asking about convolution, the intrinsic properties of the data. So yeah, you are right. So here we don't look at any of those. So in some sense, the hidden layer norm thing is kind of like a normalization of the data, but it's a normalization with the features. So which is actually probably kind of captures something like that, right? So if you normalize the pixels, then it's just a simple whitening normalization. But if you normalize the hidden activations, then you are using the structure of the data, but in a very implicit way, which we don't necessarily understand very much. So, so the short answer is we don't understand much, but I think some of this does contain a little bit in that direction.
I'm curious if you have any view on, say, the generalization properties of algorithms other than, say, stochastic gradient descent, maybe like a second-order method, or if you've thought about that approach as well.
Yeah, so I think definitely have thought about it because I think a few years back we are trying to do this second-order optimization algorithm. This is a paper that we wrote like probably 3 years ago, and what happened was the following. So actually, before writing the paper, we ran a lot of experiments. We had some new idea to do a second-order algorithm that can be feasibly implemented on neural networks, which is not trivial because when you do the second-order, Hessian is too big, so you have to do some tricks to kind of implement it. And we had this algorithm, and we thought it's going to work, and we tried it, and with some tuning, we can make the training work, but the generalization never works. So we still write a paper just because we published the theory. And we hope that this can also be useful for other things, where you don't have this regularization issue, right? So, so basically, in the paper, we only claim that we can train faster. That's also, progress, but it doesn't solve the deep learning issue, right? So, so I think from that experience, kind of, my take is that somehow the second-order algorithm sometimes is it kind of like it lacks the noises in the SGD. So, but you cannot just add noise back by kind of adding noise, kind of like spherical Gaussian noise. So, somehow the covariance of the noise in SGD somewhat useful. I don't know exactly what it is. So I think this is a common problem with many other algorithms, like for example, this SVRG or like a Saga or whatever, like this variance reduction algorithms, like SVRG stands for stochastic variance reduction algorithm or something like that. So, so all of these kind of reduce the noise too much early on, so that you lose the regularization effect of SGD. But we don't know. But I don't think we understand why the noise is fundamentally useful. So it's just an empirical kind of like a phenomenon. Somehow we see the larger the noise is always better. So, but we don't understand why it's better. Yeah.
Does that hold true if you add in these regularizers?
For the SVRG? Yeah, we haven't tried yet. So I think it's going to help the regularization a little bit because we see that it can help the generalization for low learning rate, but we didn't try it. But also because it cannot even recover the low learning rate case fully, so I probably would think that it wouldn't recover the generalization for SVRG as well. Probably it helps a little bit like this, but not that much yet.
Is that with the same amount of regularization though? Like, could you increase the regularization if you have a lower learning rate?
Yes. So yes, I think we didn't tune the parameters that much, but we did try to. I think that's a great question. So, but I think we did try tune the regularization for particularly this experiment. So this is the best trade-off we had. I think there's another question.
Do you think are some important math or statistic background for working with deep learning theory or deep learning optimization?
So do we need any statistical backgrounds for? Sorry, what was?
Or like what kind of backgrounds are important for deep learning theory?
I think for optimization, if one day we can disentangle the optimization statistics, and then hopefully, I hope, studying optimization wouldn't require too much statistics, because it's not like it's not like the statistics. So I like statistics, but I mean, it's always better to just only have one thing going on, right? So, and then for studying a statistical background, I think for this kind of like a theory, I think it's pretty much like here what we are using are this kind of like statistical learning theory type of kind of tools, which are like 20 years ago they are developed by Peter Bartlett, like in statistics. So this I think these are, I wouldn't say they are the classical statistics, but they are kind of core statistical tools. Yeah. Any other questions?
So I have a question about your experiments. Can you give us more details about how you set up the experiments? For example, how you tune the tuning parameter. I'm asking this question because there are many students who are not familiar with deep learning experiments.
Oh yeah, this is there is nothing super magic here. You just add this thing in the loss, and then you do auto differentiation. So actually, and then when you tune the hyperparameters, you just do cross. Actually, we don't even do cross validation. We just use the fixed validation set, which does it seems a little bit kind of like simplistic, but actually now these days we know that actually this is actually probably a good idea compared to cross validation. So you just tune it based on the validation error, and actually the hardest part is that to implement this this thing with the right package, because some of these packages has bugs, and and they don't do the second order derivative very well. Because here even the loss function has the first order derivative, and if you compute the gradient of the regularizer, you're gonna have to compute second order derivative, and some of these actually all the packages we use, the PyTorch, right? So it depends on version, and some version has bugs, and some version may not have bugs, but we just have to trust it, like, because there's no any other better versions. Anyway, yeah, I like to complain about it, but I guess this is on record anyway. Okay.
Okay, so let's thank the speaker for
Okay, thanks.